Hello, friends. This is Jim with Science Talk, and it's probably going to be a lengthy video. Probably already saw it from the timestamp, but I'm going to discuss with you isotopic fractionation. Now, I've already done a video some time ago where I at least introduced the general idea behind isotopic fractionation. What I want to do in this video is build on that prior video and then share with you some actual data and explain further how isotopic fractionation is used, and I'll be focusing on reconstructing past climates. So as a result, I'm mostly going to be concentrating on oxygen for this video. I'll have a few things to say about carbon, but mostly this discussion will be focusing on oxygen. So, just to a general setup here as to what isotopic fractionation is all about. Basically, it's the enrichment of one isotope relative to another in a chemical or physical process. Two isotopes of an element are different in weight, but not in gross chemical properties, which are determined by the electrons. And by the number of electrons, typically how many are in the outer valence state. However, subtle chemical effects do result from the difference in mass of isotopes. Isotopes of an element may have slightly different equilibrium constants for a particular chemical reaction, so that slightly different amounts of reaction products are made from reactants containing different isotopes. What that means is that if you have a process such as photosynthesis, how the plants use C12 or C13 is affected. Now I'll have a little bit more to say about that in a moment. So this leads to isotopic fractionation, the extent of which can be expressed by a fractionation factor, alpha, also known as a separation factor or enrichment factor. This factor is the ratio of the concentrations of the two isotopes in one compound divided by the ratio in the other compound. The other compound is typically taken to be some sort of a standard. The fractionation factor is the factor by which the abundance ratio of the two isotopes will change during a chemical reaction or a physical process. So let's just scroll down a little bit here. As an example, the precipitation of calcium carbonate from water is an example of an equilibrium fractionation process. During this precipitation, oxygen 18 is enriched by a factor of 2.5% relative to the lighter, more common isotope oxygen 16. The fractionation factor depends on the temperature and consequently can be used as a means for determining the temperature of the water in which the precipitation occurs. This is an important sentence now. This is the basis of the so-called oxygen isotope geothermometer, i.e., constructing past climates. Now, you heard me mention about carbon just a few moments ago. During the process of photosynthesis, carbon-12 is the most common isotope of carbon, is enriched further relative to the heavier isotope carbon-13 or 14. The cellulose and lignin in wood from trees is enriched by a factor of about 2.5% during this process. The fractionation in this case is not an equilibrium process such as in as oxygen in calcium carbonate, but is a kinetic effect. The lighter isotope proceeds faster through the photosynthetic process and consequently is enriched. It's kinetic because there are actual chemical reactions taking place. The organism is photosynthesizing, so there's chemical reactions going on. That will further enrich the C12 because it can cycle through faster, preferentially selected. Whereas here, with say foraminifera, absorbing seawater to form their calcium carbonate shells or tests. That's a one-time deal. It forms this. It's not a continual chemical reaction. Pull the water out, you make your shells. It's deposited, precipitates, boom, done. Same thing with forming snow that falls and compresses over time into ice. So, physical processes such as evaporation, condensation, and thermal diffusion may also result in significant fractionation. For example, oxygen-16 is enriched relative to the heavier oxygen isotopes in water evaporating from the sea. On the other hand, any precipitate is enriched in the heavy isotope, resulting in a further concentration of oxygen-16 in atmospheric water vapor. In other words, as more O18 is pulled out to form shells and tests, that means is the likelihood of more O16 going into the atmosphere is increased. That's what they're saying. And hence the enrichment, further concentration of oxygen-16 in the atmospheric water vapor. Because the processes of evaporation and condensation tend to occur in the equatorial regions and polar regions respectively. Snow in the polar regions is depleted in oxygen-18 by about 5% now compared to the surrounding ocean. As the ratio of oxygen isotopes in precipitates is sensitive to small changes in temperature, small changes, at the time of deposition, measurements of polar ice cores are useful in studying climate change. That's kind of what's going to be the basis for this discussion. Okay, let's, that's this technical paper there. So, I want to go over to here. And I'll come back to this other one in a moment. The extent of isotopic fractionation, in this case of 14C to 12C ratio, which must be measured accurately, is approximately double that for the measurement of 13C 12C ratio. If isotopic fractionation occurs in natural processes, a correction can be made by measuring the ratio of the isotope 13C to the isotope 12C in the sample being dated. You're talking about, this is how we accurately use carbon-14 dating. The ratio is measured using an ordinary mass spectrometer. The isotopic composition of the sample being measured is expressed as, and get used to the symbol here, right? That symbol there, right? That little, it looks like a little squiggle there, whatever, like a Hershey kiss, that's delta. We commonly call that del 13C, which represents the parts per thousand difference, or per mil, between the sampled carbon-13 content and the content of the international PD8 standard carbonate. So this is a difference. It shows, that's hence the fractionation. It shows the change, whatever the change may be, up or down, more positive, more negative, what have you. A del 13C value then represents the per mil deviation from the standard. And the standard, the PD8, refers to the Cretaceous belemnite formation at PD in South Carolina, USA. So fractionation can describe variations in isotopic ratios of carbon brought about by non-natural causes, such as non-photosynthetic processes. So I don't want to get too technical here because this stuff is extremely technical. And if any of you are interested, let me just pull these up here. Stable isotope processes in the water cycle. This is a lengthy paper that goes into very technical, detailed discussion as this one here. This one gets into the calculations. If any of you are interested in looking at these papers, please leave a notification for me in the comments section, and I'll be happy to supply you with the URL. Okay, and let's see. I want to show you this here. So we're talking about the del values. Whether a del value is positive or negative is less important than the relative change in del when interpreting data. Less important. We're looking at the relative change compared to the standard. So isotopically heavier means that the sample is enriched in the heavier isotope, resulting in a positive increase in values. The values go up. Now, it could go up from minus 2.5 to minus 2.2. Might still be negative, but the relative change is a change of positive 0.3. That's the important thing. Isotopically lighter are samples enriched in the lighter isotope, and that can result in a decrease in value. So you might go from minus 2.5 to minus 2.7. The change is minus 0.2. Okay. Now let's look at oxygen. The oxygen isotope ratio. Okay. This is how we calculate the del 18O in per mil, parts per thousand, is we take the ratio of 18 to 16 in the sample, and we subtract from that the ratio of 18 to 16 in the standard. So if this standard has a greater value than the sample, this is how you can end up with negative results. We then multiply by 1,000 and then divide it through by the ratio of the 18 to 16 standard, and that gives us the fractionation value, the del 18O fractionation, what the change is. So think back to your basic arithmetic. What's the change in price? Okay, you have the new price minus the original price divided through by the original price to multiply by 100. Boom, right? So it's kind of that idea. So this here is a mass spectrometer. This is a photo of a mass spectrometer. And these are complicated, delicate machinery that do precise work. I was part of research teams studying sea ice in the Chukchi and Arctic Ocean. Oftentimes we would have samples that we brought back to mass spectrometers we had in our lab. And we were looking at O18, O16. We were looking at hydrogen 2 to hydrogen 1, basically deuterium. So we were looking at those guys. We had a bunch of mass spectrometers. We also had a bunch of gas chromatographs. Sometimes you have a machine that's called the GCMS. It's a combination gas chromatograph and mass spectrometer. The research that we were doing, we didn't have such a machine as it was not necessary. Either the mass spectrometer or the gas chromatograph on their own was sufficient to give us the information, the data we were after. And by the way, some of the isotopic work that we did, as an example, we were able to discern that where the Mackenzie River flows into the Beaufort Sea, the Arctic Ocean, that one little branch of it kind of moved immediately to the west, kind of hugged the northern coast of Alaska, went around the northwestern end, down through the Chukchi, down through the Bering Strait into the Bering Sea. We were able to know that because we were tracing the isotopic signature. So these are precise machines, and they can measure very fine, precise measurements, fractionations, if you will. So it's not just whole numbers here, but we're talking 2, 3, 4 decimal places, as are our calculations. When we calculate these things here, right, we get like 3 or 4 decimal places here, which allows us to recreate a graph such as this. This is a very important graph. This is like a temperature scale. The concentration of 18O in precipitation decreases with temperature. In other words, the colder it gets, the less 18O we find. The graph shows the difference. Remember, this is a delta 18O is a difference calculation. It shows the difference in concentration in annual precipitation compared to the average annual temperature at each site. The coldest sites in locations such as Antarctica and Greenland, polar regions, have about 5% less 18O than ocean waters. And this graph is from a paper Giselle et al., 1994. This, what I'm going through here, comes from a lecture at the Geology Department at the University of Texas. So let's look at this graph here. Here's the del 18O on the vertical scale. And you'll notice the values that go from 0 to -6 down here. Temperature goes from -60 to +20. And as you can see here, it says exactly what this description says. As it gets colder, the del 18 gets less and less. It decreases. The difference keeps going down. Now, there's less and less of the stuff here. So if you measure, you can get, say, minus 3.51. You can kind of say, well, it's going to be, the temperature is going to be about, say, minus 35 C or so. You can actually use this to get a temperature reading. So when we measure these here, we can then take whatever the values we have calculated, look at our thermometer, our table of values, if you will, and we say, oh, the temperature, therefore, at that location, at that time, was such and such. Very powerful tool. So when people tell you, you guys are guessing at past temperatures, it's a load, it's a crock. We know what we're doing, and we measure this precisely and accurately. Okay. So, just want to jump up here a bit in case for some of you who may not be familiar with what isotopes are. Atoms of all matter on Earth are made up of nucleus and electrons, right? We all know that atoms make up matter. Atoms with the same number of electrons and protons but have different number of neutrons are called isotopes. Usually an atom is overall neutrally charged. Protons carry a positive charge, electrons a negative charge. The number of protons equals the number of electrons. It all negates each other out. Now, the number of protons determines the element, and we call that atomic number. So if I have 6 protons, an atom that has 6 protons will always be a carbon atom. An atom that has 8 protons will always be an oxygen atom. You change the number of protons, you get a different element. And by the way, in between 6 and 8 is 7, which is nitrogen. So, atomic mass is the sum of protons plus neutrons. So I could have, and let's look at the example, 16O. Well, there are 8 protons, so 16 minus 8 is 8, and therefore 16 oxygen has 8 neutrons to go with the 8 protons. If I go to oxygen 18, well, 18 minus 8 is 10. We now have 10 neutrons, still have the 8 protons, has to still be oxygen. So the 2 extra neutrons makes this heavier. That's basically what that idea is. The relative amounts of these 2 isotopes in a sample of water, ice, rock, plant, human, in your bones, for example, is a function of the climate environment in which these amounts show up. The relative amount expresses either the fraction 18O to 16O or simply del 18O. Now, of all the oxygen atoms found in nature, 99.8% have the 8 neutrons. 16 oxygen. The remaining 0.2% is 18 oxygen, has the 10 neutrons. So it's a very small amount, 1/400th about. Okay? But that small difference allows us to do amazing scientific work. And so here's the formulation I showed you earlier as a picture of the mass spectrometer. Okay, now, isotopic fractionation. The enrichment process. The lighter 16 oxygen evaporates first. The heavier 18 condenses out first. In other words, any oxygen 18 that does make it from the water body, be it a lake, an ocean, that does make it into the atmosphere will condense out first because it's heavy and will flop out first. Okay. But more of the 16 will be present in the atmosphere and usually be as part of water molecules, so atmospheric water vapor. So oxygen 18 is preferentially removed relative, everything, remember, this is everything relative to oxygen 16 by precipitation. Hence, the 18 is depleted, the 16 is enriched. Del 18 becomes more negative because it's depleted. It becomes more negative because it's relative to 16. But now, as the more 16 goes into the atmosphere, that does what? Of the water molecules left behind in the water, the liquid state, the 18 is enriched relative to the 16. So hence, the del 18 will become more positive. That's because the 16 is lighter, so it's more likely to escape into the vapor state. That's kind of the idea. So now what happens is, as you, and let me go down to the next thing here. As more and more snow falls and it doesn't melt, what's happening is we're leaving relative to the water behind. The 18 in the water keeps getting more and more positive. And then the organisms in the water will take up those shells, will take up that 18O and put it into their shells. So what we usually see, I'm kind of giving away the game right away with doing the synopsis, but basically, as we look in the ice core, the del 18 gets more and more negative during an ice age because it's less and less 18 relative to the amount of 16. But the 18 that's left behind in the water, the liquid state, there's more of that relative to the 16. The organisms are more likely to take up the 18 when they make their shell. So we see the del 18 go up in the shells of organisms during ice ages. So del 18 goes down in the ice cores and up in the shells of the animals during ice ages. And then there's a reversing during the interglacial because then the ice sheets start to melt. It then dilutes the water so that the O18 is now less abundant relative to the O16. And then we see a switching of the values of the del 18. The del 18 will start to increase in the ice cores during interglacials, and the del 18 starts to decrease in the shells of the organisms. Okay. So what's happening here, here's the equator down here, here's the North Pole up here. So this is like a quarter of a pie, what have you. So we start seeing, the net transport of water vapors. You have atmospheric processes, Hadley cells, that kind of stuff. And so you get some escape and some precipitation, and then some of the water vapor that persists in the atmosphere is transported to higher latitude. It falls as snow. The snow compacts into ice over time, and you can see these are values of the del 18 values. And so here are some typical values going from poles, middle latitudes to the tropics. And as you can see, surface ocean, maybe 0 to -2, +3 to +4. That's the more 18 relative to the 16, and far less 18 relative to the 16 in the polar ice. And here are some photos of microscopic organisms. These are the shells that the organisms will build, and this is where we measure typically either silicate, if it's like a diatom, or calcium carbonate for other organisms like forams and foraminifera. We just call them forams for short. Or coccolithophora, we call them coccoliths for short. It's a mouthful. Diatoms are phytoplankton typically found in high latitude waters, such as the Gulf of Alaska and Bering Sea, those kind of things. And they make tests out of silicon, so silicate shells. And again, we can see some of the values. The ice sheets about -30 per mil in Greenland, -55 per thousand in Antarctica. Oxygen isotope ratios as a thermometer. Up here, this is basically, we just saw the really negative values like -30, -55. So this is saying that the del 18O is really, really less than the del 18O at the mid latitudes, which is really less than the del 18O at the equatorial regions. So the 18 oxygen content precipitation at the given latitude decreases with decreasing temperature. Basically what's going on there. The less 18O found in the glacier ice, the colder the climate. And don't remember, in order to form these glacial sheets, what happens? Sea levels drop. Because we're taking the water from the sea and we're putting it in the ice. Little insect life form here. So when that happens, again, the amount of 18 relative to 16 goes up in the water. The amount of 18 relative to the 16 in the ice goes down, and it goes down drastically. That's the basis here. So now the long-term del 18 trend in the deep ocean as measured from the calcite shells of foraminifera, forams. Now, you have to keep in mind there are two forms of foraminifera. You have planktonic, which are the ones that are floating in the water column, and you have benthic, which are those that are found in the substrate. And they can yield two different results. We'll be discussing that in a bit. So, what do we have here? We have here on the vertical scale millions of years ago, so starting from present day, and let's see, and going to 70 million years ago, and we have a deep water del 18 values going from +3 to about -2. So, long-term trend in the deep ocean. Changes in the deep ocean temperatures, growth of ice sheets on land, which will enrich this 16 oxygen. And as we can see here, you have some Antarctic ice present. There's no known ice from about 40 to 70 million years ago. And we see what? Look at what the values do. Right? As you cool down, right, you are enriching in the water the 18. And if you look at the scale here, going positive is to the left. Kind of counterintuitive, but that's how they set up this figure here. And we see what? We see there's a cooling down going on, maybe a little warming, and another cooling down. Additional cooling of the deep water. Ice sheet growth and greater than 7 degrees C, additional cooling of the deep water. And basically, to taken as this looked like about 2 million years ago or so, and that's pretty much about when the last ice age, the Earth started coming out of the last ice age. Okay, so let's take a look at this graph here. And what we're doing here is we're showing that using the oxygen isotope as a thermometer. And this is going back for a long ways, from present day back to basically the time of the Cambrian explosion 542 million years ago. So this is million of years ago on the horizontal axis. So here we have like the Cretaceous, Jurassic, Triassic, so forth. Carboniferous, Devonian, Silurian. So now we're looking at the del 18 oxygen on the vertical axis, and I have some notice here. Keep in mind, this is looking at the del 18 in the water, not the ice, in the water. We've already established that the 18 is enriched relative to the 16 in the water during glacial or colder climates, because more of the 16 escapes, falls as ice, it falls as snow, becoming compacted into ice, and as more 16 goes into the atmosphere, and don't forget the water level, these sea levels are dropping, the O18 relative to the 16 keeps going up. So the more positive the values, and positive values are going down this way, the more positive the values, the colder is the climate. Warmer values, meaning that the 18 in the water is being diluted by the 16. And we look at the graph here, the blue is the short-term average, the black is the long-term average. And what do we have here? Okay, really cold, warming up a bit, cooling down a bit, warming up a bit, gets really, really warm here, and we see this cycle. See the cycle of temperatures over time. And as I showed you earlier, we can recreate the temperatures based on our del 18 signature. Now, if this was a plot of del 18 oxygen in the ice cores, then we would see what? We would see more negative values when it's cold and more positive values when it's warm or hot. Now, it'd be like you just change the signs on the numbers here. So, and this goes back quite a way, but yeah, you can see the cyclical nature of the temperatures there. And that's, probably due to certain factors such as Milankovitch, which I will be discussing in an upcoming video. So anyway, now we can look at some other aspects of using isotopic fractionation to help tell us of what was going on in Earth's past. All right, so colder temperatures, more oxygen depletion in the ice. Right? It's important to make that distinction. Condensation preferentially removes the heavier isotope. Evaporation preferentially removes the lighter isotope. I should say lighter here. Okay. So temperature, colder temperature, there's more oxygen depletion in the ice, but enrichment in the water. And vice versa. Warmer temperatures, more oxygen enrichment in the ice, depletion in the water. Remember, this is relative to oxygen 16 because it is not, it's what, 0.2% of the oxygen isotope is the 18 variety. Okay, I want to show you, I think it's over here. Yeah, this is a picture of an ice core. Well, several pictures of an ice core. And this is an Antarctic ice core. This is basically 53 to 54 meters. I don't know if it's visible on your screen, but if you look closely, you can see some lighter patches, darker patches, lighter patches. You can see this little dark line there and so on. You can see some patterns of light and dark. Get further uh, into the core, deeper down, you can definitely see the striations. Now, there might be some soot, there might be some sediments, as definitely from down here, it looks like there's a lot of sediments that got into the ice. But in all these things here, we can take a little sample there, and we could run into the mass spectrometer, we can run it into the gas chromatograph, we can measure oxygen, we can measure hydrogen, we can measure CO2, you name it. We can measure a bunch of things here. And we can then create a profile. This gives us a profile of the past climates. Right here, seriously. What we do. So, I want to go to here. And this is kind of a recap, a reiteration. Climate temperature from ice cores. Ice in glaciers has less 18O than seawater, but the proportion of heavy oxygen also changes with temperature. And it is very sensitive. That's why I say we can get to 1/10 of a Fahrenheit degree with 100th of a Celsius. We can get to that kind of precision, that level of precision. To understand why it might be so, we need to think about the process of glacier formation. The water ice in glaciers originally came from the oceans as a vapor, later falling as snow, becoming compacted in ice. When water evaporates, as we've been saying before, the heavy water 18, H218O is left behind. The water vapor is enriched in light water, H216O. Any water molecule containing 18O will precipitate out quickly, leaving behind the water molecules with the 16O to travel north and be deposited as snow. So again, any water containing 18O that does evaporate quickly condenses out as rain. This is simply because it's harder for heavier molecules to overcome the barriers to evaporation. It's harder to get into the atmosphere. Thus, glaciers are relatively enhanced in 16O, while the oceans are relatively enriched in 18O. This imbalance is more marked for colder climates than for warmer climates. In fact, it has been shown that a decrease of 1 part per million of 18O in ice reflects a 1.5 degrees C drop in air temperature at the time it originally evaporated from the oceans. Okay, let's highlight that again. It has been shown that a decrease of 1 part per million 18O in ice reflects a 1.5 degree Celsius drop in air temperature, basically 2.7 degrees Fahrenheit, at the time it originally evaporated from the oceans. Now, this is a snapshot. Simple measurement of the isotopic ratio of 18O in ice cores can be directly related to climate. Ice cores from Greenland or Antarctica are often layered, and the layers can be counted to determine age, like I showed you in those photos. The heavy oxygen ratio can then be used as a thermometer of ancient climates. So now, if we look at the global ocean ice water budget, water is evaporated from seawater. The oxygen in this water is enriched in the lighter 16. This condenses in clouds falling on land's precipitation. I've already discussed that. Thus, water that is part of the terrestrial water cycle is enriched in the light 16 oxygen isotope, and seawater is enriched in a heavier 18 oxygen isotope. Glacial ice is therefore made up primarily of water with the light 16 oxygen isotope. This leaves the oceans enriched in the heavier or more positive. During glacial periods, more 16O is enriched in glacial ice, and the oceans become even more enriched in 18O. During interglacial periods, the 16 melts out of the ice and the oceans become less oxygen 18 rich or more negative in it. That's what I was talking about earlier, how the values would then start changing around. And now, the same isotopic analyses can be made in ocean sediment cores on the shells of dead marine organisms. Some of these organisms are made of calcium carbonate, calcite, and the oxygen in the carbonate reflects the isotopic abundance in the shallow waters where the creatures live. Thus, if we can find and date ever more ancient sediments made up of old seashells, we can determine the isotopic ratio of oxygen and infer the sea surface water at the time. In other words, basically, they are referring to the planktonic forms that, as they die, they sink through the water column and then they land on the substrate, and then over time they get compacted down, and any other sediments that come from the rivers that go into the ocean and settle out will cover them. So when you get compacted down, you can take an ice core and look for these things. So the more 18 oxygen found in the sediment, the colder the climate, which is the inverse to that of the glacier ice. So we have two means to verify our results. Oh, we have a really low, really negative delta 18O in the ice, and oh look, we have a more positive del 18O in the sediments or in the shells. They help verify and corroborate the results. Very important. So now I want to go to here, and a lot of this is going to be similar discussions. Here's this, they have a slightly different formula. This is sort of the same thing if you look at the other formulas for calculating the fractionation, be it 13C or 18O. Okay. Oftentimes you will get a negative number. Not always, but oftentimes. And what they're talking about here in oxygen isotope has been what we've been discussing thus far, so I won't go over that again, but I do want to look at this graph here. This is a really excellent figure, and that helps pull together all the things we've been talking about as far as what's going on in the liquid water part of things. So, when the Earth begins to warm, ice caps begin to melt back. If the Earth warms further, there are hardly any permanent ice sheets at the poles. When this happens, the O16 enriched ice returns to the ocean as water. Thus, a high influx of water enriched with O16 creates ocean waters that then become diluted with respect to O18. On the chart on the right, warmer times are indicated by more negative or lighter O18 values in the water, not the ice, indicating a reduction in the amount of ice on the Earth. The above scenario applies to global oxygen values of the oceans. Isotopic values of oxygen can also be measured from different regions and compared for the same time in Earth's history. So we can get global results, and then we can get regional results and can do comparisons. And that is very helpful, useful information. Regionally negative del 18O signals, which is more oxygen 16, can indicate that an area experienced increased rainfall. So before we look at this figure here, let's talk about benthic and planktonic foraminifera. Then we'll look at the carbon isotopes. Because the ocean bottom water is more homogeneous, it's very dense water, well mixed, compared to surface ocean water. There's, you have more changes in density at upper water layers than you do at bottom water layers. Benthic forams record global isotope values. We'll refer to this here in a moment. The figure at the right shows the Del 18O values from benthic forams for the last 10 million years. It goes from 10 to 0 at the top. So, and when they typically look at these graphs, they go from oldest to youngest. To interpret what's happening, let's begin at the bottom of the curve and work our way upwards towards the younger date. Note at the bottom of the curve, values are in the red color with more negative values. This indicates that at this time, which is the Miocene, the bottom ocean temperature was much warmer and thus there was less ice at the poles. As you move up in the curve, the values fluctuate quite a bit, but in general, it trends to the right in the blue area. This means the values are becoming more positive for Del 18O relative to 16, which indicates there's more 18O molecules in the water, which is interpreted to mean the Earth was cooling down and there was more ice at the poles. Remember, if the Del 18 is increasing in the water, we should see a corresponding decrease in the Del 18 in the ice cores. This is looking at the water. And if we're looking at the forams are incorporating the oxygen into their shell, which is a reflection of the environment they were in. And if there's more 18 in the shells, that means the Earth was in a warmer, there was more 18O, so the Earth was in the cooler times period. Yeah, I cannot stress the importance. 18O, Del 18O increases as the Earth cools down, which means the Del 18 in the ice decreases. Increases in water, decreases in the ice during cooling down periods, and then it decreases in the water, increases in the ice during warming periods. That is the take-home story. So we start from here. Okay. We have what? This is telling us that it was considerably warmer, much less ice at the poles. And as we go this way and this way, it's getting cooler, which means there's probably growing some more ice at the poles. More oxygen 16 equals warmer, less ice. More oxygen 18 equals colder, more ice. So I would prefer to have seen less oxygen 18 equals warmer, less ice. This would not be as confusing. But that's what's going on. So we have this data that tells us what's going on with the planet. Then we can take the actual Del values, looking at the layers and so on, going back to that chart I showed you earlier, and then say, oh, the temperatures were thus and thus. Give us a global average. Then we can go to specific regions, and then we can construct by region what's going on. Okay. Planktonic forams. Oxygen curves from planktonic form record a more local signal. So the benthic forams give us the global signals. Planktonic gives us a more local signal due to surface waters being very dynamic, quite heterogeneous, so on. Curves from planktonic forams can be interpreted the same as benthic forams in general, but the effects of evaporation and precipitation can also affect the isotope signal. It gets a little trickier to tease out that signal. Evaporation causes a decrease of O16 ions and an increase of O18 in the water column, which causes the curve to move towards more positive Del 18 values, and precipitation increases the amount of 16 ions in the water, which causes the curve to move towards more negative. So you get a little more fluctuation with the Del 18 values when you look at planktonic foram because of the ever-changing dynamic. It's like record the temperature at a location over 24 hours. You're going to have a lot of wide fluctuation. But now, what's the do that every day, and then what's your climate? What's your average temperature? Kind of the same idea here. Now let's look at carbon isotope. Now, carbon is trickier, as I mentioned at the outset. The photosynthetic process itself can widely affect the del 13 carbon. So, carbon isotopes obtained from the shells of marine organisms are strongly influenced by photosynthesis, respiration, and upwelling. Upwelling is the vertical movement of water in the ocean. Water comes from deeper depths and comes up to the surface, which means that continuity of volume consideration, the surface water spreads out and has to sink somewhere else. When a planktic foram builds its shells in an upwelling area, the del 13C will be more negative. And that's because when water upwells, older, more enriched C12 water comes up from the bottom to the surface. So in other words, the C12 dilutes the C13. Hence, the del 13 becomes more negative. Now, throughout Earth's history, the amount of carbon 12 and carbon 13 in the atmosphere and the oceans has changed, makes working with the carbon isotopes trickier. A little more difficult working with that. However, I can say this. We have the ability, using isotopic fractionation, we have the ability to tell you where the source of every single CO2 molecule. We take a CO2 molecule, we can measure its isotopic signature. We can tell you if that was the result of a biological process, such as a respiration from an animal, or decomposition of, let's say, when the permafrost thaws, or if it's the result of burning fossil fuels. We can tell you that. So, and actually studies have been doing this, and studies are showing that more and more of the CO2 molecules in the atmosphere are showing more and more signals of being a result from fossil fuel burning. This is another reason why we know that human activity is definitely causing the planet to warm because of isotopic analyses. So let's look at this del 13 again in benthic organisms. It looks like it's going from minus 1.5 to 2 on the top there. And the vertical scale is again millions of years, going all the way down to, looks like 10 at the bottom. So same scale as that one. Okay. Positive carbon 13 equals younger bottom waters, higher sea levels, less erosion from land. Negative carbon 12, older bottom water, lower sea level, more erosion from the land. Because you put more material in, you're going to displace the water. But here's the interesting thing. We can use this information to ascertain sea level heights. How much the sea level has dropped, that sort of thing. We can tell that. Okay. So let's just go through a little summation of, come on, scroll down. Why doesn't want to scroll down? Okay. Increased or heavier del 13C values generally indicate increased productivity in the ocean. Photosynthesizing organisms preferentially uptake C12 during photosynthesis, but leaving the C13, the heavier one, in the water column, with which marine organisms build their shells. When there's a lot of photosynthesis happening in the water columns, that's increased productivity. Therefore, that leaves more 13C in the water column that the organisms then incorporate into their shells when they build them. So when there are times of increased productivity, lots of things growing, photosynthesizing in the water column, this usually means there's an increased burial of carbon or sediment accumulation on the seafloor. Right? Organisms die, they sink to the seafloor. So if they die and they die with increased C13 in their shells, that means they died in a water column that was quite productive. By the way, this data comes from Zakos et al., the 2001 paper. That's what this figure comes from. So an increase in del 13 values can also indicate that erosion from land is decreased. Soil tends to have a more negative del 13 value because it contains remains of dead plants. When the soil washes into the ocean, it puts more C12 in the waters. So what happens if we have decreased C13 values? If there's little photosynthesis occurring in the water column, there's more C12 molecules in solution, and thus more are incorporated into the shells of marine organisms. This can correlate with times of decreased burial because there are not as many organisms living in the water column. Del 13 C values can also become more negative due to increased erosion from land into the ocean. CO2 from volcanoes tends to be enriched in C12. So times in Earth's history that are characterized by intense volcanism can create more negative del 13 C values. Another factor that needs to be considered. So if we now look at the benthic forams, carbon curves created from the benthic foram shells tells us what's going on with the bottom water conditions. Respiration, or the decay of organic matter, tends to release more C12 into the bottom waters. Water masses move along the seafloor. They pick up this signature, which gets incorporated into the benthic foram shell. Thus, a benthic foram's del 13 C value can tell us the age of the bottom waters. Older bottom waters picked up more C12, which equates to more negative del 13 C values. And the reverse for younger bottom waters, more positive del 13 C values. So again, looking at this curve, we're seeing what? We're seeing a general decrease in the del 13 values over the 10 million years. From I think it's really a lot of signals, but it's a general decrease. And that tells us what? There's less photosynthesis going on. So there's a little summation here. And we can look at the planktonic foram, similar for oxygen isotopes, carbon isotopes obtained from planktonic foram. Again, more local signal versus a global signal from the benthic, just like with oxygen. So in this summation here, benthic forams, okay, the more negative it is, we have decreased ice volume. This is in the water. Okay. The more positive, colder, because then what happened? There's more 16 in the ice on the land. So the del 18, this is for the water, is more negative during warmer global climate, decreased ice volume. More positive during colder global climate, increased ice volume. If this were del 18O from ice, more warmer, then it's going to be more positive, colder be more negative. If it was for ice, the reverse, remember. That's the benthic foram. The planktonic foram tells us basically the same thing, as well as increased local precipitation, increased local evaporation. Looking at del 13C in the water. And when we say in the water, we're basically also, this is, looking at what's in the forams. Those are the foram. We're taking this out of the water. Okay. The more negative it is, the bottom waters are older. That means there's more increased weathering. More positive, is younger bottom waters, decreased weathering. And that also, when we look at the planktonic, decreased local productivity, increased upwelling, increase local productivity, decrease or no upwelling, low local productivity. So decrease productivity, increase productivity, and we look at the values there. So just to kind of pull that together, I want to go right up to the top here. Okay. Heavier Del 13C values increased, right? Generally indicate increased productivity in the ocean. So when there's a lot of photosynthesis, then there's a lot of increased productivity going on, and we see that accumulation on the seafloor. An increase in Del 13C values indicates erosion from land is decreased. Okay. So looking at the Del 13C values, we can get an idea of the conditions of the ocean, what kind of productivity was happening. And we'll look at that graphic. Notice that Del 13C values in general from 10 to 0 million years becomes more negative. This signal is in part from the bottom ocean waters becoming older as the modern day deep water ocean circulation began. The youngest waters sink in the Arctic and travel along the bottom of the water column into the Pacific Ocean. This is basically was starting, when you start thinking about it, the Earth really started entering in the cooling down phase over the last several million years. And we're actually seeing this with our isotopic signatures. And part of this is when the Isthmus of Panama closed off, prevented further equatorial water flow, created the Gulf Stream. Now that brings warm water to the polar region where latent heat energy gives it off to the atmosphere, and boom, it starts snowing. And you start growing ice sheets, and you form a deep water formation. And I discussed with you that the mechanisms behind that. So, start seeing an overall trend of decreasing Del 13C values, indicating younger bottom waters and higher sea levels. So, again, we can precisely reconstruct past situations in the ocean, past climates. We can do so globally and locally. We look at the Del 18 oxygen signal during ice ages. The Del 18 oxygen gets more and more negative in ice. The Del 18 oxygen in the sea water, as measured by the forams and other organisms that absorb the oxygen 18 into their shells, that Del 18 oxygen increases. Then during warming periods, the reverse. The ice, the Del 18 oxygen in the ice gets more positive, gets more negative in the water, in this measured in the test. And that's because the melting ice, liquid water, then dilutes the O18 relative to the O16. So we can, looking at this here, we can look at this. That's a general figure, but this gives you an idea what the temperatures are in the past, based on the measurement of the Del 18O in ice. And looking at the Del 13C, we can tell you what kind of activity was happening in the oceans, was upwelling, and the nature of the bottom water, that kind of information. So I think I'll end this here. I kind of been going at this for a wee bit. I hope you found this informative and interesting. I thank you for your time. I thank you for your patience with this. So until the next time, take care. Hey folks, this is Jim here reminding you to subscribe to this channel, to share my videos, tell others of the work that I do here. I also ask that if you are not already a patron at Patreon, to please consider becoming a patron at Patreon. You can find the information in the description box below the video. I'm asking you to help support the work that I do. I do not take any money from corporations or from any other sources, so the information I share with you is the actual science as it comes out of the peer-reviewed journals. So there is no BS, there's no propaganda, there's no agenda. It's just I present the science and I explain to you what it means, or at least my interpretations of it, based on my own experience as a scientist. I want this channel to grow. I consider, while I discuss many different topics here, you notice I do focus a lot on climate issues. I consider climate change to be the most pressing issue facing humanity today. Thus, I consider it important to disseminate this information to a wider and wider, more and more people. And I need your help to do this. So, yes, please subscribe. Please tell others of the work that I do here. Please share my videos on social media platforms, with your social media groups, what have you. We need to get this information out there. So for those of you who are supporting me on Patreon, I thank you greatly for your support and continued support. It does mean a lot to me. So together we can get this information to more and more people. Thank you. Thank you for your support.